Hello, calculus fans. Now remember that if we have a vector field, big F, and it has a scalar field, little f, for which big F is equal to the gradient of little f, then we say that big F is conservative. In this case, we call little f a potential function for big F. In this case, there is a theorem that lets us to easily calculate line integrals of big F. That theorem is the fundamental theorem of calculus for line integrals. And it says that if you have a conservative vector field with a potential function, little f, then to evaluate the line integral of big F, then all we have to do is evaluate little f at the end of the curve minus little f evaluated at the beginning of the curve. So here C is just some curve with a parameterization R of t, and the parameter values go from A to B. Now here's the important fact about line integrals through conservative vector fields. The value of the integral only depends on the starting and the ending point. This is called path independence. It doesn't matter what path you take, it only matters where you start and where you end. And of course, the value of the integral can be very easily calculated if we have a potential function. Unfortunately, if our field is not conservative, we can't use the fundamental theorem, but of course, it's still possible to evaluate the line integral using our computational formula. This is the formula that we've been using as a computational formula up to this point. This computational formula requires that we have a parameterization of the curve, and it also requires us to compute an integral. That, of course, could be difficult or very messy to do. And of course, coming up with a parameterization often can be difficult. So in general, we're going to want to compute line integrals through conservative vector fields because the calculation is going to be so much easier. Okay, that's all for now.